All right, so when you notice walking up to it, you have a x times a function of x. So it's a product of two variable functions. There's no product rule. So the first thing I would do is rewrite it with the 5 out front. You got an x times 2 to the 3x squared. Now, because that's 2 to the blob, it's not just 2 to the x. It would be a good candidate for U-substitution, but whether we use it or not, we have to figure out, bless you, what the outside function is. So the more complicated of the two factors is, of course, the second, 2 to the blob. That's our outside function, 2 to the blob. Therefore, the inside function in what we would call U is 3x squared. Now, the pattern recognition would be just to check, did the other factor of x come from the chain rule when we were unpacking boxes? Well, what's the derivative of 3x squared? It's 6x to the first. So you're like, yep, we got it. That's it. That's where that x came from. So we're ready to go to our answer. The 5 goes along for the ride. He's your rider. We have a correction of what? If we generate an unwanted 6, we have a correction of 1/6. There's the correction. Okay. And now we go to the rule of anti-differentiation. 2 to the blob is exponential, right? So what would be the antiderivative of 2 to the blob? Well, if it were e to the blob, if it were e to the x, the antiderivative of e to the x is itself. So if it's not base e, it's going to be itself again, 2 to the blob. But there's going to be something else involving the natural log of 2 that I'm not sure what to do with yet. So I'm just going to hold off on the natural log of 2. I'll put a little note. Do I multiply or divide by it? Well, for now, I'm just going to make a note. And I'll leave my blob right here and then plus c. Okay. So this is going to be my guess. Now, when I check it, I'll take the derivative. So the 5 and the 1/6 go along for the ride. What would be the derivative of 2 to the blob? Well, the derivative of 2 to the blob is 2 to the blob times the natural log of 2, right? I know that when I take the derivative of exponential and it's not base e, I multiply by the natural log of the base. And then it would be times the chain rule 6x. And then, of course, the c goes to 0. So the 1/6 and the 6 divide out, and I get the exact same thing I started with, except looking back now, I have an extra unwanted natural log of 2, which is a number, right? And so now when I come back up here and I do my revision, the 5 as the rider, the 1/6 as the correction was good. The 1/6 corrected the unwanted 6. But now, how do I correct an unwanted natural log of 2? Divide by the natural log of 2 or put its reciprocal 1 over the natural log of 2 in front. So that's like another correction. And then it would be 2 to the 3x squared plus c. And there's your answer. All right. So these types of problems don't show up a whole heck of a lot when it's not base e. If that had been e to the 3x squared, then our guess would have been correct. All right. But when it's not base e and it's exponential, you always generate another unwanted natural log of the base when you check. So you'll just have to have an additional correction of 1 over. All right. If you were to do the U substitution, it would look pretty much the same. You would say let U equal 3x squared. And so now we're going to have, bless you, 5 times the integral of, it would be 2 to the U. And then when I take the derivative of this, the derivative of U is going to be 6x to the first dx. That's in differential form. And now I need to solve for x dx. So x dx is 1/6 du. And now I can replace both of these with just a 1/6 du. And now when I bring that out front, I get 5/6, the integral of 2 to the uth power du. And now I've got it down to just a single function without an embedded function. And what's the antiderivative of 2 to the u? Well, it's itself, but even then I have to remember there's an additional correction of 1 over the natural log of 2. And then the 5 over 6 goes along for the ride plus c, and then you substitute back in. Okay, so that's how you do that. All right, so good little warm up with exponential that's not base e. Okay, questions on that one? Oh, I took the derivative. That was me. The derivative of u with respect to x is just 6x, and then I multiplied both sides by dx. Yeah. I know I'm gonna have to take the derivative. That was just me taking the derivative in differential form. You don't have to do that. You could do it in 2 steps. Take the derivative, Leibniz notation, and multiply both sides by dx. Okay. This should hopefully start getting easier and easier for you the more we do. All right, so this one number 5, that's what we're on. You got a pi in the bottom, you're divided by pi. So I would pull that out front as a 1 over pi. You have the product x plus 1, which is already in parentheses. Part of the rewriting, I would take the thing under the radical, x squared plus 2x, and say it's to the 1/3 power. All right, now without expanding, I can't really expand. I have a product of 2 variable factors. The second factor looks more complicated. And so walking up to it on the outside, blob to the 1/3, that's probably going to be your outside function. And so what would the inside function potentially be? It would be x squared plus 2x. Let's check. Let's check. And you don't even have to write this down, but I will. I'm going to be writing down when I'm checking in my head. What's the derivative of x squared plus 2x? Well, it's 2x plus 2, right? Is that where the 1x plus 1 came from? Well, yeah, if you factored out the 2 from your derivative, you get 2 times x plus 1. That's exactly where the x plus 1 came from. We are just off by a 2. We're off by a factor of 2. We generate an unwanted factor of 2, which is really not a problem because all we have to do is correct it. At this point, when you hit the variable part of the other factor or factors, you know you've got it made. All right, so you can go right to your answer. The 1 over pi goes along for the ride. You make your correction of a 1/2 because you're off by a 2. And once you put your correction down, now you can transition to the rule of integration, which is involving your outside function. Blob to the 1/3 by the power rule, leave a space. It's blob to the 1/3 plus 1, which is 4/3 times 3/4 in front, and then plus c. And oh, by the way, what goes in the parentheses? The blob. And there's the answer. All you have to do is clean it up. Right? Cleaning it up will look like this. You have 3 over 8 pi, and then you can put this back under a cube root of the quantity x squared plus 2x to the 4th power plus c. And of course, if you're unsure about it, you could check it and then come back and revise. You can always revise. If you're only off by a constant multiple, remember, you can always revise it by putting the reciprocal back in your guess. If you're off by more than a variable, still when you check it, then when you go back and revise, you got to look for a totally different way. You got to look for a different rule because you misidentified one of the functions, or there's another way to do it that you're not seeing. Okay, it's going to come down to, do you recognize it as the derivative of something? Can you use the power rule, or can you manipulate it into something that resembles one of the other two? Everyone okay? This is the writer. This is my correction. And this is my rule coefficient. Those are the only 3 types you'll ever have. And then you're not necessarily guaranteed one of each type every time. Again, as we do this, if you're still kind of, it takes a while for you to get comfortable with it. If you force yourself to check by taking the derivative of what we have here, you'll see it play out going forward and how we end up with what we're given originally. And you'll be like, oh, that's where that came from, or that's why that goes away. Okay. All right, I'm not even going to do the U-substitution. Example 6. These all look very similar, but there's a slight difference on these. So we'll just kind of go through these quickly. You've got product of two variable functions, right? So step 1, bring the 5 out front. Rewrite anything if you need it. Sine of 2x, that looks good. Times e to the cosine of 2x, that looks good. Dx. So really that first line was just to bring the 5 out front. Which factor looks more complicated? Yeah, good. It has 3 layers actually. So the outer layer, e to the blob. Okay, and by putting extra parentheses there, you're helping yourself see the inside function. So e to the blob is probably going to be your outside function, and therefore that's going to be the rule of integration. Now we just check what's inside the e function. Well, there's 2 functions inside of it, right? Cosine and 2x. So here you have a double inside function. Let's check. What would be the derivative of cosine of 2x? Well, the derivative of cosine of 2x is negative sine of 2x times what? 2, right? Or negative 2 sine of 2x. Do we get the all-important variable part? Yes, we get the sine of 2x. What we do get, though, also is an unwanted negative 2. But that's not really a problem at all. An unwanted negative 2, we can correct with the reciprocal of it. So that means we've got it. 5 goes along for the ride. We're off by a negative 2, so we have a correction of a negative 1/2. And now we're done with the first part of this integration. Now we move on to the outer function, the e to the blob. And easier than the warm-up, but similar to it. What's the antiderivative of e to the blob? E to the blob. We don't need to divide by the natural log of e because it is its own grandpa and grandson. And then plus c. And you're done. That's it. Don't trust yourself. Don't believe me. Unsure. Take the derivative using the chain rule, and you'll see it lines up. Now, again, the last thing you could do in each case is to clean it up. Negative 5/2 e to the cosine of 2x plus c. You know, getting rid of some of the parentheses, combining some coefficients. There you go. It's fun. It's easy. It's becoming fun easy. Right now, it's just fun. All right. Questions on that one? Part B. All right. You got a product of 2 variable functions again. Sine of 2x, cosine squared of 2x. Step 1, constant multiples out front. Rewrite anything that needs rewriting. So we got a 7 integral sine of 2x times, and here I'm going to write this as cosine of 2x, but now it's all to the what power? 2/3. Good. Dx. Second factor obviously looks more complicated. So if you walk up from the outside, you say, what's up, blob to the 2/3? And that's your outside function. So your inside function is probably cosine of 2x. Let's see. At this point, you don't just jump right into the antiderivative using the outside function. You always check. The first part of these types of problems is to actually take a derivative. The derivative of cosine of 2x is negative 2 sine of 2x, just like before. And once again, we get the critical variable part, which is what we need. We're only off by a negative 2 once again. So it means we've got it. So 7 goes along for the ride, a correction of negative 1/2. And now the rule of integration, which is really what varies from one problem to the next. Now it's a power rule, right? Blob to the 2/3, leave a little space. You get blob to the 5/3 times 3/5 plus c, and then the blob just drops right in there. And you're done. That's it. It works. Take the derivative to verify if you want. Now, cleaning up, let's see what we got here. Cleaning up, we've got a negative 21 tenths times the cube root of, and we'll write that as cosine to the 5th of 2x. So it starts in radical form, will end in radical form, but rational exponent form on the in between. Okay, and there again, we had one of each type of coefficient. We had the rider of 7, the correction of a negative 1/2, and the rule coefficient of 3/5. Questions? Okay, number 2. Hey, same idea. 2 variable factors, 2 out front, sine of 2x times cosine of 2x, quantity squared. All right, so in that time, I went ahead and just wrote the outside function already with its own separate color. And check this out. Not surprisingly, the derivative of the inside function is negative 2 sine of 2x. We're off by negative 2. Okay, now some of y'all might say, hey, we're not off by a negative 2. We're only off by a negative, right? Because there is a 2 that's there. If you want to let that 2 be part of the derivative, that's fine. Go for it. Just don't mess up. I don't think it's even worth doing that analysis because it's all going to work its way out in the end anyway. I'm just going to say the 2, he's already used up. He can't be part of the derivative of the inside function because he's already in the back of the truck. Too late. 2 goes along for the ride. And now I'm off by a negative 2, so I'll have a correction of negative 1/2. Either way, 2 times negative 1/2 gives you a negative 1. If you had let the 2 be part of the derivative and you say you're only off by a negative, you would have a negative correction, but now you'd have to let the 2 kind of be carried away with the antiderivative. Okay, and then we go to the rule of integration. It's going to be times 1/3 blob cubed. And the blob just gets dropped right in there, plus c, and you're done. You're done. Or as I like to call it, negative 1/3 cosine cubed of 2x. Just a final way to package it. I'm going through at a nice even pace, but if you have any questions or you want to see it using U-substitution, just holler. The more we work, and if you understand each one, then the more we work, the better, the easier it gets. All right, look at this one. It almost looks like a misprint, right? Sine of 2x times sine of cosine of 2x. Okay. Nothing really needs to be rewritten here, but you might want to like add parentheses to help yourself see inside functions. Now there's 2 factors here. You got this factor and you got this whole factor. So again, the second factor looks more complicated because it has an extra layer. So the outside function on the second factor is sine of blob. Sine of blob. And what's inside of it? Bless you. There it is again, cosine of 2x. So notice it's been the same inside function for all of the problems so far. The only difference is the rule of integration because it's been contained inside a different outside function. So yeah, we know this. We get a derivative of negative 2 sine of 2x. And so we're off by a negative 2. There is no rider this time other than a 1. So we go straight to the correction of its reciprocal, negative 1/2. And then we move on to the rule of integration, which is the green part. It's inside the sine function now. So what's the antiderivative of sine? Cosine? All right, let's try cosine. It's negative cosine. Yeah, negative cosine of the inside function plus c. Well, the inside function is also cosine. So cosine was the inside function. It was also the rule of integration. And again, don't put dot negative, put it in parentheses. Hopefully, if you did say that the antiderivative was just regular cosine, you would have checked. Notice that you were still off by a negative. You would have gone back and revised it, because these make good multiple choice questions. And of course, both of those would be there. Just an FYI, right? If you're given one of these as a multiple choice question and all your answer choices are possible antiderivatives, sometimes it's easier just to go through and take the derivative of each of your answer choices and see which one matches up to your integrand. Back solving, right? So this ends up being positive 1/2 cosine of cosine of 2x plus c. Nice. Okay, and then this guy here, probably just outside the scope of AP. We'll put it like this: AP with the circle around it and a line through it, like not quite AP. Here you have a quotient, right? And you're like, whoa, there's a lot going on here. So step one, too much fun. Step one, I might notice that there's a 2 factor in the top and a 3 factor in the bottom. So I can pull a 2/3 out. And in the top, I'm left with the sine of 2x. And then in the bottom, I would need to possibly bring it to the top anyway. Bring it to the top, and that would be the entire quantity to the negative 1/5 power. And then inside there, you'd have cosine squared minus sine squared. So I'm guessing the outer function, since the second factor is the more complicated of the two, the outside function is going to be blob to the negative 1/5, which means the inside function then has got to be cosine squared minus sine squared. Well, what's the derivative of cosine squared minus sine squared? Is it sine of 2x? What? It's a double angle identity. Yeah. If you take the derivative as that is, you're going to get this. You're going to get 2 cosine of x to the first times the derivative of cosine, which is negative sine of x, and then minus the derivative. You're going to be like, whoa, that's not sine of 2x. But if it's a problem that you're expected to know how to do, then there's got to be something else going on. And there is. This is the double angle identity. So here they are again. You need to have these memorized. Sine of 2x is 2 sine of 1x cosine of 1x. And this one, which looks a lot like Papa Pig, except it's got a subtraction in the middle, that's the double angle for cosine. Cosine of 2x is cosine squared of x minus sine squared of x. In alphabetical order like that, C before S, cosine before sine. So once we do that, that's the key that we need to unlock this fantastic door. With fun on the other side, that's cosine of 2x. And now you're like, oh, okay. Now I know why it's in this section, because cosine of 2x is your inside function, and its derivative is negative 2 sine of 2x. And yep, we're only off by negative 2 once again. So 2/3 goes along for the ride. We have a correction of a negative 1/2. And now on to the rule of integration. Blob to the negative 1/5, leave a space, is blob to the add 1 to get 4/5 with the reciprocal in front, 5/4 plus c. And oh, by the way, the inside function is still cosine of 2x. And there it is. Clean it up later if you want, but that's it, right? Nice. So you can see one of the strategies we did there. We had a quotient here. We haven't seen too many quotients, but remember that division is just multiplying by the reciprocal. So to put it kind of on that same level playing field, bringing your quotient or your denominator into the top to turn it into a product, that's not a bad strategy. So that we can start looking at it as, is one of them the derivative of the other? Okay, turn a quotient into a product. All right, now let's look at the last one here. This one, I'm running out of room, so let me just copy it and paste it over here somewhere. Well, let me add a page. Another page. There's not enough on this assignment. This one will be close to the record. All right, so I spy an 11 that's coming out front. Yep. And now we got sine of 2x times cosine of 2x. Now this one's a little bit different from the others, because now if I asked you which of those factors looks more complicated, the sine of 2x or the cosine of 2x, you'd be like, I don't know. You got a coin I can flip? I don't know. They both look equally easy, right? But if you follow kind of what we've been doing in all these other problems, the previous 5, the inside function has been cosine of 2x, right? Cosine of 2x. So I guess cosine of 2x could be the inside function. But now here's the question. What the heck is it inside of? A power of 1. Very good. Those can be kind of the hardest to see because they're not there. They don't need to be there. But it could be inside blob to the first. And now if we do that, we're like, oh, okay, now I got it. The derivative is, -2 sine of 2x. I'm off by a -2. So 11 goes along for the ride. We have a correction of the reciprocal of the unwanted -2. And now we move on to the outside function, which is the rule of integration. Blob to the first becomes blob to the second. And then divide by 2 or multiply by a half plus c. And oh, by the way, the blob is cosine of 2x. So that's certainly one way to do it. And in all the other methods up above, like the ones that had square roots and stuff, we had to choose cosine of 2x to be the inside function. But because they're both to the first power, we also have another option. Watch this. Or we could say 11 sine of 2x, cosine of 2x. But you could have just as easily have said, okay, sine of 2x could be inside something to the first now. And now your inside function could be sine of 2x, possibly. What's the derivative of sine of 2x? Cosine of 2x times 2. I do generate the other factor, but now I'm only off by a 2. So now the 11 goes along for the ride. I have a correction of a half. And now the rule of integration is blob to the first becomes blob to the second times 1/2 plus c. And oh, by the way, this time the blob is sine of 2x. Which one of these is the correct antiderivative? They both are, yeah. Now, if two functions have the same antiderivative, does that mean that the antiderivatives have to be the same? No. An antiderivative, good.
I saw it there, I kind of thought it would be possible to take 2 different derivatives or any derivatives of a different problem as well. Is there multiple for every single one of them?
Oh, for the every single one that we've done?
Yeah.
Well, let's look at this one up here on in part C.
I think that was the one that I thought.
In this case, the second factor has a squared on it. So could we do this? Could we say that sine of 2x is inside something to the first? Well, let's see. What would be the derivative of sine of 2x? It would be 2 cosine of 2x. Are we only off by a 2? No, because I generate only a cosine of 2x and I have to generate a cosine squared. And I'm off by a factor of cosine of 2x, which is a variable. So no, All the others that we did up here, they only work one way because because the exponent was something other than one. Yeah. All right.
The exponent's the
But
same.
when the exponents were the same, it can go either way. Yeah. Now, here's the deal. If one function has two different looking antiderivatives, then they only differ by a constant, right? Which is the vertical shift. They only differ by a plus c. Let's take a closer look at that. If I simplify this, I get negative 11/4 cosine squared of 2x plus c. And over here, I get positive 11/4 sine squared of 2x plus c. These should only differ by a constant. Let me show you what I mean. If I do a Pythagorean substitution down here, if I replace sine squared with what sine squared is equal to, by the Papa Pid, sine squared of blob is equal to 1 minus cosine squared of the same blob. That's using a Pythagorean substitution. And now if I distribute, I get 11/4 minus 11/4 cosine squared of 2x plus c. And oh, by the way, what is 11/4 a constant plus an unknown constant? It's another constant, isn't it? So I get this new and improved constant called c sub 1. Okay, jam wow. And is that the same thing as I have over here? Yes. Now those constants aren't necessarily the same. So they only differ by a constant. In this case, you can see they only differ by the 11/4. So you can have a function with two different antiderivatives, but if they are different, then they only differ by a constant. Okay. So both of those methods are correct. All right. So sometimes you do have flexibility, but sometimes no. Sometimes no. All right. Questions on example 6. It was kind of helpful to see same inside function, but rules of antiderivatives were different. All right, example 7. This kind of goes to what I was speaking. Evaluate two different ways. Show that they're equivalent, but for a constant. I'm not going to do that because you would do it the same way that we just did using the Pythagorean. But I will show you that this one has two different ways you can find the antiderivative. All right, so walking up to this fella, you might want to rewrite the secant squared. Right? It's just kind of a natural reaction to write it in expanded form. Now, if you're going to do that, you would say then that your first factor probably looks more complicated, right? And then you would say, okay, what's the outside function? It's blob squared. Well, that would then mean that secant of x is your inside function. Now, here's the deal. If secant is your inside function, we would need to check, is that where tangent came from? What's the derivative of secant? Secant tangent. Oh, crap. Are we off by only a constant? No, we're off by a whole secant. You're like pooper scooper, right? But so I can't just go 1/3 secant cubed, right? Darn. But if you see why this one fails, you can modify it. You're like, man, wouldn't it be nice if instead of just a tangent there were a secant tangent there? Wouldn't that be nice? Well, you're like, hey, I have a couple of secant factors over here. So what if I just associate them differently? What if I call secant squared secant of x times secant of x? That's legal, right? And now I will say that secant of x is inside something to the first power. Yeah. And now my outside function is 1 degree smaller, but hey, it's going to work now. My inside function is secant. And what's the derivative of secant? Secant tangent. Am I off by anything? Nope. So there's no writer other than a 1. There's no correction to make. So I go straight to the antiderivative. The secant tangent gets packaged back up. So what's the antiderivative of blob to the first? 1/2 blob squared plus c. And what's the blob? Secant of x. Let's see. So there's one version of the answer. You can write it as 1/2 secant squared of x plus c. That's one version. But there's another way to do it also as well, additionally too. Secant squared of x times tangent of x. What if we say tangent is actually the inside function? What would it be inside of again? Well, it would be inside something to the first power. That would make tangent the inside function, of course. And then what would the derivative of tangent be? Secant squared. Hot diggity donut. Are we off by anything? Nope, not a thing. So there's no writer other than a 1. There's no correction to make. Secant squared gets packaged back up. And now we're on to the rule of integration. Blob to the first becomes 1/2 blob to the second plus c. And of course, the blob is tangent of x. And if you simplify, you get 1/2 tangent squared of x plus c. And there you go. Those two guys right there are they're not the same, but they have the same derivative. They only differ by a constant. And if you want, you can kind of show that by using baby PID number 1, 1 plus tangent squared of x equals secant squared of x. Right? So for what it's worth, here's the other one, right? 1 plus cotangent squared of x is cosecant squared of x. And what the heck? Cosine squared of x plus sine squared of x is equal to 1. So there's your 3 PIDs again. You probably know them, but when they come up, if we just write them every time, because it doesn't take long. And the more you see them, the more you know them, right? Do a little substitution, one of them distribute, and you see that they differ by 1/2. Okay. Nifty. Fun, 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 fun. We're done with page 4 of 12 now. Wow. Moving right along. Example 8. Okay. So now we're getting into the level of sophistication that we started the notes with, but we're going right to the integral instead of here, take the derivative and then integrate. Looking at this guy, I see how many factors that are variable factors. I got an x squared, I got a 5 to the blob, and I got a secant squared of blob. So here I have 3 variable factors. There can only be one big box. So all but one of those variable factors have to be derivatives of the other factors inside function. We're only off by a constant multiple. Okay. So step 1, bring the 4 out front. Okay. Now, if you want to wait to get to the answer to do that, that's fine. There's no rewriting that needs to take place in the way through there, or does there? Oh yeah, there does actually, right? Yeah. Let's see. 4 out front. Boom. We got x squared times 5 to the x cubed plus 7 times. Now, secant squared is interesting because you can think of secant squared itself as the derivative of tangent. In other words, secant squared is its own antiderivative, but you can also say that it is inside the blob squared function. So however you want to handle it. So if you did get in the habit of writing everything that's in condensed trig form into expanded trig form, that's what you would write it as. Okay, so let's go ahead and do that. Now, of course, the third factor is more complicated. So doing what we've done so far, here's what you would probably tell yourself. You walk up to the outside function, and that would be blob squared. If blob squared is the outside function, then everything inside of it would be the inside function, and we check. That means secant would be part of the inside function. What would be the derivative of secant of blob? Secant blob, tangent blob, right? Do I have a secant blob, tangent blob factors outside? No, I don't. I don't. If I had another secant blob, tangent blob out there, I would have identified it correctly. So that means that we need to take a slightly bigger bite. Okay. And that means that blob squared is not the outside function, but secant of blob is the outside function. Okay. Now, if secant of blob is the outside function or secant squared is the outside function, you're going to have to know how to anti-differentiate secant squared. And we do. It's the derivative of tangent. So that means then that just 5 to the blob is the inside function. And let's check. Let's check. What would be the derivative of 5 to the blob? 5 to the blob times the natural log of 5, which we don't have there, right? So we're off by a natural log of 5 times the derivative of its little inside function. The derivative of x cubed plus 7 is 3x squared. And we're off by another 3. So we get the x squared part. So notice the way I did that, I only wrote down what we were off by. But we do generate the other two variable factors, yes? And that's good. So that means we've identified our inside and outside function correctly. So now we're ready to go to the answer. 4 goes along for the ride. We have 2 corrections to make, don't we? From the first layer, we are off by a natural log of 5. So I have to have a correction of 1 over the natural log of 5. From the second layer, I'm off by a 3. So I have to have an additional correction of a third. So there's 2 corrections to make. Once you get rid of all your corrections or done with all your corrections, you just move on now to the rule of integration. The inside functions are contained inside secant squared. What's the antiderivative of secant squared? Tangent of the blob plus c. And the blob is just 5 to the x cubed plus 7th power. And there's your answer. Clean it up if you want. Take the derivative to verify if you want. Don't forget the plus c, don't forget the plus c, don't forget the plus c. Okay. See, so not as bad as it was when if we would have tried example 2 right off the bat. All right, y'all try this one on your own, part B on your own. You don't have a lot of triple factors on the AP exam like this one. So if you can handle this one, I feel pretty good for you. All right, so I brought the 22 out front. E to the blob, the derivative of the blob, the derivative of cosine of blob is negative sine of the blob. So we're off by a -1 times the derivative of the blob, which is 15x squared. So we're off by a 15. So we get it. We're only off by a -15. 22 goes along for a ride. We get a correction of a -1/15. And now I move on to the rule of integration. What's the antiderivative of e to the blob? E to the blob plus c. Oh, and what's the blob? Cosine of 5x cubed. Kaboom, that's it. That's the answer. Yeah. All right, pre-cash, I will pay the guy, not off, but I will pay the guy, and we'll make sure that we get the screens lowered.